All right, everybody, hello and welcome back. Today what we're going to do is we are going to continue solving nonlinear systems, but now we are going to do elimination. So if you think back to our previous lesson together, this was a problem that we worked on where we went ahead and we substituted one equation into the other. Since we know what y is equal to, we can take what it's equal to and plug in. All right, but we can also use our other methods. It really kind of depends on the setup of the problem. In this case, we can also use our next method of solving systems, which is elimination. Now, in this case, everything works out pretty well for us because if you take a look, our values are lined up. That means we have x squares over each other, we have our x values, our constants, and then our y's. All the variables that we have are kind of organized nice and neatly into rows, so we can go ahead and solve using elimination. Now, what I need to do is I need to get one of my variables to eliminate the other when I add them together. And now I'm going to do that by multiplying my top equation by -1. All right, when I do that, I will get a positive 2x squared minus 4x minus 2 equals -y. And now what I can do is add those two equations together. When I do that, I'll add my x squares and I will get 3x squared. I'll add my x's to get a -6x, and then I'll add my values to get positive 3. All right, now when I do the same thing with my y's, they end up eliminating each other, and now I am left with a quadratic set equal to 0, which is great because I can go ahead and solve. Now, we've solved this already. It's actually the exact same quadratic from before, but we were able to get rid of one of our variables using a different method. We were able to get rid of it using elimination instead of substitution. So this process will lead us to the same solution. Now, I wasn't going to do it, but why don't we just go ahead and quickly solve. We get x squared minus 2x plus 1 is equal to 0, and we divide out a GCF. And then we factor into x minus 1 times x minus 1, which is still equal to 0. And we get x equals 1 as our solutions. We need to plug back in, which we can quickly do, to our bottom equation. And we are left with a solution of 1, 4. So again, I wasn't going to work all the way through this because from this point on, it's the same as our last one. But the point I wanted to show is whether we use elimination or we use substitution, we should be getting the same answer. So it really doesn't matter which one you use. It kind of just matters how the problem is set up. You know, in this case, it could be either elimination or substitution. Now, this one is a little bit more clear, in my opinion, why it should be elimination, because again, everything is lined up the way we might want. No variable is isolated, so I wouldn't use substitution here. If you notice, our y values are already opposites of one another. So all I have to do is add these two equations together, and we've eliminated one of our values. So I can move everything to one side, and now we can solve. So I can't factor this, but let's just go through an example where we use the quadratic formula. I have the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So I'm going to get x equals 7 plus or minus. Well, my discriminant's going to be 49 minus 24, which is 25. And the square root of 25 is 5. So I get x equals 7 plus or minus 5 over 6, or x equals 7 plus 5 is going to give us 12 over 6, which is 2. 7 minus 5 is 2 over 6 is 1/3. So I'm going to take each of these x values and plug back in to find my solutions. So I have 2 times, let me do the bottom equation. 2 squared minus 2 times 2 plus y equals 0. 4 minus 4 plus y equals 0. Well, these cancel. I get y equals 0. So one solution is going to be 2 comma 0, and the other is going to be a little bit more challenging because we're squaring a fraction. And because I'm running out of room there. Here, I'll rewrite that so we get a little cleaner work here. So we have 1/3 squared minus 2 times 1/3 plus y equals 0. So this is going to be 1/9 minus 2/3 plus y equals 0. All right, let's do a little common denominator work here. 1/9 minus, well, to get a common denominator here, I have to multiply 3 by 3 to get 9. So if my denominator is going to be 9 and I multiply this by 3 to get it, I need to multiply my top by 3, and this will be 6/9. All right, and then I get negative 5/9 plus y equals 0, or y equals 5/9. So my solution here is also going to be 1/3 and 5/9. So these are the two solutions to my quadratic system. All right. We've got one more example we're going to take a look at, and it is y equals negative x squared plus 4, y equals negative 4x plus 8. So this one's a little bit different. I would probably use substitution here because we can just take what y is equal to, and plug right in. However, I want to show you how we could use elimination for it as well. What I'm going to have to do is kind of reorganize these a little bit. I'm going to write y equals negative x squared plus 0x plus 4 instead of my top equation. Now, normally I wouldn't need 0x here, but I'm going to use it as a placeholder. And then my second equation is y equals 0x squared, because there is no x squared in it, minus 4x plus 8. All right, so now everything's kind of lined up. I am going to manipulate one equation to get it by itself. I am going to multiply my bottom equation by -1. We get negative y equals 0x squared plus 4x minus 8. So if I add those two equations together, my y's cancel. I will get negative x squared plus 4x minus 4. I can divide by -1 first to get 0 equals x squared minus 4x plus 4. And this is going to factor into x minus 2 times x minus 2. All right, so that tells me that I get x equals 2 as a solution, which I can plug back into one of my equations to get the corresponding y value. So my solution for the system is going to be 2, 0. So these are the examples we're going to take a look at. I want to remind you that not every system has a solution. We could have a system that has a quadratic and, let's just say, a linear function that never intersect. Now, what that would look like is it would look like a quadratic similar to something we had over here, but we'd end up with a negative value underneath our square root, which means the solution would be imaginary. If that's the case, we are not going to continue to solve for imaginary values. Instead, we are going to say that there is no solution to the system because there is no real point where the equations are going to intersect. Okay? As always, thank you for listening. If you have any questions or concerns, please feel free to reach out.